Hey guys, in this video, I'm going to show you how to perform a ductile damage simulation using Abaqus. So in this model, I'm going to have a ball travel at very high velocity to penetrate a piece of plate. So to do that, let's create the parts first. Right click, create, and then the name is going to be our plate. I'm going to use the shell function, planner, continue. Then I'm going to create a rectangle shape. Then after that, we can use the dimension function. The plate needs to be 60 millimeter by 60 millimeter. So 60 here and 60 there. And then okay. So now we got a plate. So let's check it. All right, looks good. The next part is our ball. So right click, create. And then the name is going to be our ball. I'm going to use the shell function again. I'm going to use the revolution. The approximate size, I need that to be 10. I don't need 200. So continue. Then I'm going to draw a circle from our center point here. Then we can again using the dimension function. The diameter I need is 4 millimeters. So 4. So after that, I'm going to draw a line to cut the circle in half from here to here. Then I can remove the lines I don't need. I don't need this line. I don't need this line. So as you can see that right now, we only have the half circle left. So I'm going to have this half circle revolve along this construction line for 360 degrees. So hit OK, OK. 360 degrees to make a circle. All right, so now we have the ball. And now we have to define the material properties for our parts. So to do that, we go to our materials, double click, and then the name is going to be our plate. And we define the mass density. So in here, I'm going to use a 0.1 grams per cubic millimeter because the unit here is a kilogram. So that's why for 0.1 gram is going to be 0.0001. So after that, we need to define our elastic characteristic. So for the Young's modulus, I'm going to use the number from our stainless steel, which is 210E3 millimeter square. For the Poisson's ratio, it's going to be 0.3. So we got the elastic, and then we need to do the plastic. So for the plastic, I'm going to use this number. The maximum plastic strength is 0.5 here. Then we have to define the material of failure criteria. So to do that, we go to mechanical, the damage for the ductile material. And then the fracture strength. The fracture strength happens after the maximum plastic strength. The maximum plastic strength is 0.5. So that's why in here I'm going to use 0.6. The stress triaxiality is the ratio between the combination of your principal stress divided by your von Mises stress multiplied by the constant of 1/3. Because we are using the isotrophic material here, so I think I'm going to assume that the combination of my principal stress is equal to my von Mises stress. So that means that in here, the stress triaxiality, I can just use the constant of 1/3. So for the strain rate, I'm going to assume that there is no variation here, so it's going to be 0. Then we have to go to the sub options, the damage evolution. For our damage evolution, we assume that everything is based on the displacement, so everything is linear. And then for the displacement at failure, I'm going to choose 3. The number here is correlated to your mesh size. So the mesh size I'm going to use for this model is 2.25. So that means that I am allowed my material to be stretched a little bit than its original size. Then you will have some failure. Then I hit OK. Okay. So after the material of the plate has been created, we need to create a material spec for our bowl. So to save some time, I'm just going to copy the one we have here, and then I'm going to rename that as bowl. Hit OK. So I'm going to keep everything the same, but I'm going to change the density to make my bowl material to be 10 times heavier than my plate, so the bowl can carry a higher momentum. All right, hit OK. And now we have to define a section for our parts. So to do that, we go to the section here, double click. So the name is going to be plate, shell, homogeneous, continue. And then the value, I want my shell thickness on the plate to be 4 millimeter. And then the material is going to be my plate. Then OK, right click, create. And then the second one is for our bowl. Again, a shell, homogeneous, continue. So for my bowl, I want the thickness to be a 1 millimeter thick. So the material is going to be our bowl. So after those being created, we need to apply those sections onto the geometry. So to do that, under the bowl here, then we go to the section assignment, and then we select the geometry, hit OK. The section is going to be our bowl section. So I want my material to be offset up to my top surface. So all my material will be inside the bowl geometry. So hit OK. So we can verify that. Let's see the cross section, and then we can see the thickness rendering. So view, part display option, and then render shell thickness. All right, so everything is inside my geometry. So this looks good. So the next thing is that we need to apply the section to our plate. So double click the plate, and then section assignment, and then select the geometry. Okay, the section is going to be our plate. I'm going to apply that to our middle surface. So as you can see that everything is alongside with the middle surface here. So this is good. So after that, I'm going to assign a mesh to our parts. So let's go back to our bowl first. So I'm going to double click my mesh here, and then we choose mesh, and then element type, select the geometry. Okay, so this is the explicit analysis, so that's why we choose the explicit. And explicit, this is shell material, then we hit OK. So we have to select the mesh size. So to do that, we choose the size to be 2.25, then apply OK, then we can mesh it. So now the part has been meshed. Then we have to do the same for our plate. So here is our plate. Let me turn off the thickness rendering. No, not here. Part and view, part display options. Okay. So in here, we select the mesh, the element type, then we select the part, then OK. So again here, we choose the explicit. And one more thing we need to do is that in here, the element deletion, we have to choose yes. So that means that when the material failed, the material will be deleted from our analysis. So we hit OK. Then we choose the mesh size. For the mesh size, again 2.25. Okay, and then we can mesh it. So now the part has been meshed. Alright, so the next step is to create a step. So to do that, we go to our step, then double click, then create step 1. The step 1 is after our initial step. So the analysis is going to be a dynamic explicit, and hit OK, continue. And then for the time period, I'm going to choose a 0.05 second and hit OK. So after that, we go to our field output result here. We double click. So in here, I want my analysis to have 500 data points. So that's why the interval, I choose 500. So the default one is okay, but I just need to add one more thing here. So we go to the state here, then we find something called a status. So here is the function tell Abaqus to show the material failure. So hit OK. So now we need to create our assembly module. So to do that, go to assembly, instance, and then hold the shift key. We can select both a ball and a plate, and then hit OK. So after that, we need to rotate and move the part to the right location. To do that, let's use the rotation function first. I'm going to define the rotation axis, and then the rotation angle, 90 degrees. Okay. And then I need to move that a little bit from this point to this point. And then let's do it one more time. From this point to this point. Okay. So now the ball is right in the center of the plate. The next thing is that I'm going to move the ball to be a little bit further away from the plate. So to do that, select the ball. So the first point is going to be 0, 0, 0. I'm going to move the x-axis by -50. Then, okay. So the next step is to create an interaction between the ball and the plate. So to do that, we go to our interaction properties, double click, and then it's going to be the contact, then continue, then hit OK. So if you don't define anything, so this is going to be a frictionless contact. Then we put that into our interactions. So apply the interaction on the step number 1, and then it's going to be general contact. Continue. Always self, and then we choose the property we just created, and OK. So now the interaction has been created. The ball we got here, it is a moving object, so it will keep moving. So I'm going to create a local coordinate system to move along with the ball together. So using that local coordinate system, I can better control the orientation and also the boundary condition for the ball. In addition, the local coordinate system is also very useful for the post-processing. So to create a local coordinate system, I need to define a reference point first. So I'm going to define the reference point at the geometry center of this ball. So to do that, we go to Tools, Reference Point. So I'm going to select the point right in the center. So this is going to be my reference point. So after that, again, go back Tools, and then we go to Datum, and then we select the coordinate system. It's going to be 3 points, and then continue. So I'm going to select this point. And after that, because I'm not going to change the orientation of this coordinate system, so I can hit enter, enter. Then you can see that we have a local coordinate system created, and this is based on the geometry center of this ball. I need to add a constraint to the ball to couple my element on the ball shell with the geometry center, the reference point. So after that, the ball is going to be more like a rigid body, so the ball will not crumble when it hit with the plate. So to do that, we go to constraint, double click, and then coupling, continue. I'm going to select the reference point. This is going to be our control point. And then I'm going to select the surface. I'm going to choose the purple surface because the purple surface is the inside surface. Then we select the coordinate system, use the one we just created. So it's going to be constrained on all the movement and also all the moments. Then hit OK. So in this simulation, the ball is going to impact on the plate. So other than the speed, I also want to put some rotation on the ball. So to do that, we go to the boundary condition, step number 1, and then a mechanical, velocity, continue. And then we select the region. The region is going to be our reference point 1. Because our reference point 1 is coupled with the entire shell here. So that's why if we turn the reference point 1, we are going to turn the entire ball. So okay. For the coordinate system, I'm going to choose the one we just created, the local one. So I want to have the rotation about the x-axis. So that's why in here the VR1 is going to be, I'm going to use 200 radian per second. Other than that, I also want to have another rotation about the z-axis. So the VR3, again, I'm going to use 200. So it's going to be instantaneous. Okay. I'm going to put some speed on the ball. So to do that, I'm going to use our predefined field. And then it's going to be our initial step. So in here, choose a mechanical, velocity, continue. And then we select the whole thing. And then for the speed, I want the speed to be 4,000 millimeters per second. So it's going to be moving the X direction. So hit OK. Finally, we are ready to create a job for the analysis. We double click the jobs and then continue. And then for the precision, I always try to use the double precision because it can give me a more precise result. So hit OK. Then we can run the analysis. Right click and then submit the job. OK. So the job is completed. So in our field output request, we want to have 500 data points. So that's why in here, we have total 500 row of data. So everything looks good. So we can see the result. Right click, result. So here's the final result. So let's rotate that a little bit so we can have a better view. Let's turn on the stress contour and also turn on the animation. So you can see the ball rotated a little bit and then impact and penetrate the plate. Alright, so let me do this. So as you can see that upon impact, the maximum stress we have on the plate is 720 megapascal. And then let's see the other side. So in the center, loose material got pushed and stretched. So the displacement is keep increasing to a certain point. And then you can see that loose material got deleted because loose displacement has reached to the failure criteria we define in our material properties. So we can always go back and change those material properties. So if you do that, and then you will change the final result behavior. So basically people say garbage in, garbage out. So in order to have a good result, we need to have a good material properties in order to get a good result. So I think that's all I have for this analysis. I have lots of fun working on it. I hope you like it too. Thanks for watching.